Okay, so we've gotten to the point now where we have a strategy. We have created our motion diagram. We've collected all of our information on the motion diagram. We've written out all of the information that we have in our given list, and we've written out what we need, and we've found a formula that we can use to solve the problem. Okay, and if you do this correctly and follow the pattern the way it's meant to be followed, you've done all of this without having to know necessarily how to solve the problem. Now, as you continue to do this, you will build a lot of intuition about how to solve problems in the future, but we're making it so that when presented with any problem, in this type of problem, you can solve it without being able to see how to solve it beforehand. The strategy list will just lead you through it. Okay, now what's next? Letter E here, substitute values in for the variables and solve. So once you have this formula, before you plug in values and solve, let's eliminate anything that will be a zero, and I'll show you how this works. But there will be several values that will oftentimes be zero. For example, my initial position will oftentimes be zero. My initial velocity will oftentimes be zero. And so if you eliminate those values or those variables right up front and then rewrite out the formula that you have, it'll make it a lot easier to visualize before you try to solve it. Also, I will not require you to do this, but I recommend that you learn how to isolate the variable you want to find. When you get the formula and you eliminate the zero values, one of the things that's still going to be a problem for you oftentimes is that the formula itself doesn't look like it's solving for what you want to find. Okay, the variable that's being solved for the formula says I'm trying to find whether it's the final position or the final velocity or the final velocity squared. That may not be the value that you actually want. And you've been taught in the past in algebra classes to simply start plugging values in and then solve for the variable that you want. I'm going to suggest a different approach. I'm going to suggest that you isolate the variable that you want, get the variable that you want by itself on one side of the equation, and then plug values in. This will result in you making less calculations and provide less opportunities for mistakes. Okay, now you don't have to do this. You can do it the way that you feel comfortable doing it, and if just plugging values in right from the start works. But I guarantee you, when we get into some more complex problems, that's going to become very, very confusing, and it will lead to a lot of mistakes. So every time we go through a problem, I will model this skill. I'll show you how to do this, hopefully that will become a practice that you follow as well. Okay, then also have a reasonable estimate of what you want your final answer to be. A lot of times, and I'll try to model this as well, a lot of times you'll be able to think ahead. You'll look and see, well, this answer is not going to make sense. This answer doesn't make sense. And part of that is going to be the next thing, letter G here. If you use units in all your calculations, you'll be able to see, and I'll show you this, I'll model this as well. You'll be able to see that your units are supposed to cancel out to get the units of the value that you want. So if I want position, or I want my final position or displacement, how far did I go? That needs to be in meters. And so my units, when I'm multiplying and adding everything together, have to end up being in meters. And so that can also be a good clue to help you know that you've done a problem correctly. And then finally, you have to show all this work. You can't just do part of this and then say, oh, I get the rest of this, I'm just going to write the answer out. You can't just plug values into a calculator and then just show me the final answer. You have to do all of this, or I will not give you full credit, because the problem-solving process itself, all of this stuff that we're talking about, is part of the answer that I want. Okay, you can say, well, I can do this without this. Well, maybe you can in this particular instance, but when we get to more complicated problems, if you haven't practiced doing this every single time, then it won't make sense when you get to these much more complicated problems. So you have to show all of your work. So let's practice our new skills with these problems. We've got 3 new problems here. Write these down. Write everything down the same way I do in the videos. Later on, I'll let you show me solutions however you would like, within reason. But for now, I need you to do things this way. And I promise you, even though it seems like a lot of extra writing, the strategy will pay off. Okay? So I need you to write these things down my way. Okay? So, I'm going to go ahead. I've made 3 separate little additional videos here for each of these problems that we're going to do, and so I'm going to go run these videos within the videos because I may want to make some more comments after each one of these. So I'll go ahead and start this video here.
Okay, so for this first problem, we are going to be designing a runway. Okay, you're designing an airport for small planes, and one kind of airplane that might use this airfield must reach a speed of takeoff, or before takeoff, of at least 27.8 meters per second, and can accelerate at 2 meters per second squared. Now, the only reason I put this in here, this 100 kilometers per hour thing, if the problem originally had 100 kilometers per hour instead of 27.8 meters per second. Remember that we can turn kilometers per hour into meters per second by dividing by 3.6. If we do that, we get 27.8, and we've known that trick for most of the year. Okay, so anyway, if the runway is 150 meters long, can this airplane reach the required speed for takeoff? And so when I go into these problems, I like to tell myself, I don't know how to solve this problem, because it makes me feel good when I actually do solve the problem. Go into this and say, I don't know how to solve this problem, but I know how to start.
Sorry about that. I had to blow my nose.
And I know that my strategy will lead me through the problem. And so I want to show you how that happens. So I don't have to know how to solve the problem in order to create a motion diagram. Okay, I know how to do this. I create my frame of reference with an origin at 0 and a positive x-axis, and then I start collecting information. That's the process, right? I collect information. First piece of information I collect is the initial position. And since I haven't been told what the initial position is, I can go ahead and say that the initial position is going to be 0 meters. I can make that decision. I can make whatever decision I want about the initial position. I just have to make sure that it's consistent with the rest of it. So anyway, my initial position is 0 meters. The second piece of information that I always get is, what is my final position? And I've been told if the runway is 150 meters long, so that's the constraint that I have, my final position has to be 150 meters, and by that time my airplane better be traveling at least 27.8 meters per second. I don't know how long it's going to be or how fast it's going to be going, but it better be at least 27.8 meters per second. Okay, so my next piece of information that I gather is my initial velocity, and I'm not told what my initial velocity is, but I'm assuming that it's 0, because before it takes off it has to start at 0, right? And then I don't know what my final velocity will be. I would like it to be 27.8 meters per second, but I don't know what it's going to be, so it's a question mark. That's what I need to find, is what is that final velocity. But I do know that as it's accelerating, it's going to do this. It's going to increase its speed in a positive direction. And these arrows are important for me because they tell me what the direction of my acceleration is going to be as well. My acceleration has to be in the direction of increasing length of the velocity vectors. They don't have to be going the same direction that the acceleration is. They just have to be going in the direction of increasing length. So the smallest one here, the next one, and the next one, the next one. So my acceleration has to be going in that direction. Otherwise, I wouldn't be increasing in speed like this in the positive direction. So my acceleration then, I've been told, is going to be 2.00 meters per second squared. Okay, so now that I've gathered all this wonderful information, I can write it down in a way that's useful to me. I can write it in a list. So I can say x0 equals 0 meters, x equals 150 meters, v0 equals 0 meters per second, and I don't know what v is, that's what I need, so I'm going to put that in my need list, okay, and then my acceleration is going to equal 2.00 meters per second squared. I have not been given a time. So in saying I have not been given a time, I've already figured out what formula I have to use. And I'll show you why that is in just a second, but I haven't been given time. So now I'm going to say what formula do I need to use to solve this. Okay? I don't know yet exactly how this is going to work out, but I don't need to know. I just need to know what this set of information is going to allow me to do in terms of formulas. And my first question that I ask, we're going to follow our logical questions, right? The first question I ask is, do I have time or do I need time? And the answer to that is no, I do not have time. I don't need time, but I don't have time either. So in order for me to solve any problem, it doesn't matter what it is, any problem in one-dimensional motion, in order for me to solve that problem, I have to use this formula, which doesn't require time. V squared equals V0 squared plus 2a times x minus x0. I have to use this formula. Okay, there's no choice. I do know that a couple of things have dropped out. Remember, we said that you should always start solving this by showing things that are going to end up being zero. I know that my initial velocity is zero, so I'm going to cross that out. And I know that my initial position was zero, so I'm going to cross that out. And that leaves me with v squared equals 2ax. Okay, this is a lot easier for me to see what's going on. I need this final velocity here. So in order to find that, I'm just going to isolate that and take the square root of it. And my final velocity is going to be the square root of 2a times x. So now that I've got my formula, I can take that over here and solve it. So 2 times a, my acceleration is 2.00 meters per second squared. And then x is 150 meters. Okay, now I want you to notice something here. This is why we always use units, so we can see how they actually cancel out. If I multiply the units in the acceleration, meters per second squared, times meters, I'm going to get meters squared per second squared. Well, that's a weird unit, except it's under the square root. So if I take the square root of that, I'm going to get meters per second, which is what I want. I want the velocity, right? So I know that my units work out, and that helps me to know that I'm on the right path. And if I do this, I look at my final velocity, and it's going to be 24.5 meters per second. Okay, now that's not enough, is it? It's not going to reach the takeoff speed that I need before it reaches the end of the runway. So the next question then is, if not.
So actually at this point, I'm going to need to go to the next video, and then we'll finish this problem in the next video.